Welcome to the second day of this school on synchrotron light source and its application. I am Giuliana Quilanti, and I'm now based at the International Atomic Energy Agency. And I have the honor to chair this session. Today's program is quite, let's say, technical. So this session is dedicated to storage rings and their components and on beam lines. So I introduce the first speaker, Simone Mitri from Elettra Syncrotrone Trieste, that he will do a quite exhaustive presentation on the design and operation of accelerator chain and storage ring. Simone,
thank you.
You can start.
Thank you, Giuliana. Welcome, everybody. I'm going to share my slides. And now I'm putting them in display mode. Okay. So as agreed, I will basically split my lecture in two parts so that the audience will have the opportunity to put questions after the first part and after the second part. So the idea is to give a flavor of how synchrotron light sources in particular work and the motivations and how they are built, how they work basically. So let's start from the reasons, from the motivations for such relatively large and complex infrastructures. Let's summarize the motivation of our synchrotron light sources with going back to our, if you are a physicist or engineer, maybe our background in advanced physics. So just let's consider two principles: the Heisenberg's uncertainty principle and the de Broglie particle wave duality. For those of you who are not familiar with them, you can play mathematically with them, just replacing a constant, the Planck constant, in one into the other one. And you get an easy relation between two quantities, which is the wavelength of radiation which interacts with matter, and lambda, and delta z, the scale, the spatial scale you want to investigate in your matter sample. Basically, in order to get a spatial resolution at a given delta z, you need a light at a wavelength which is characteristic wavelength, which is of the order of and possibly less than the spatial scale you want to investigate. And this is basically a very rough estimation, assuming an almost monochromatic beam, assuming the light is just at one frequency. In other words, we need X-rays to investigate spatial scales, the molecular and down to the atomic scale, as indicated in the right plot here, where, of course, because of the one of the second relation shown here, I hope you can follow my cursor. You have the shorter wavelengths for equivalent higher photon energy. So in order to access smaller and smaller spatial scales, you need the higher and the higher photon energies. And that's why we need X-rays, which have to be actually not only satisfying the requirement on the photon energy per se, but also on the distribution in space, time, and frequency, as we will see in a moment. In other words, EUV and X-rays are ideal probes of chemical bonds, where most of the science is rooted, and they help us in visualize, and this visualization should be intended in a wider sense, depending on the technique you are adopting in order to reconstruct the images or infer properties of your matter, your sample, to visualize proteins, molecular structures, atomic levels, and even orbitals, and so on. So how do we generate and use such special X-rays? The tool we are discussing, we are talking about today, is the storage ring light source in the flavor of synchrotron light source, in the flavor of a light source, advanced light source. In other words, a circular accelerator which is aiming to produce very intense and collimated X-rays. And why do we need such a tool? Well, basically, the radiation is produced in a synchrotron is due to the emission of electromagnetic energy by accelerated particles. We can calculate with, electromagnetism the amount of power we can extract from a charged particle subject to centripetal acceleration. And what we get is the formula you see on the top of this slide. So the amount of power is proportional to the fourth power of the particle energy. Gamma is the so-called Lorentz factor, which is proportional to the total energy of the particle, and inversely proportional to the bending radius. Now we can translate these physical quantities into total energy, magnetic field, which is the driving force of the centripetal acceleration, and inversely proportional to the rest mass of the particle, which is an invariant for each particle. So this expression tells us that in order to get very high power, electromagnetic power, radiation, we need very high energy, strong magnetic fields, and relatively light particles. And that's why synchrotron light sources are basically electron accelerators at very high energy and implementing strong magnetic fields. Now, as you see in this picture, there are not only dipole magnets in order to magnetic objects to turn basically the electrons. We can also invent some special arrangements of dipole magnets, and we'll talk a little bit later, and you will hear more today, which are called insertion devices like wigglers and undulators, as sketched here. Now, once the radiation is emitted, it's extracted from the synchrotron light source, which is the circular accelerator where the electrons continue being stored for hours and possibly days. And the radiation is somehow brought to a sample, to the experimental chamber along a so-called photon beam line, and the experimental chamber, that is the place where several experimental techniques can be adopted and implemented, as listed here. I'm not going to discuss about them because it's not my field, and you heard and you will hear more about them during this school. But this is more or less to illustrate how a synchrotron light source is working. Now, why accelerator-based light sources instead of maybe more compact objects to generate X-rays, like X-ray tubes? Well, the point is that basically almost all experimental techniques that I've listed before gain from a large six-dimensional photon density. In other words, you want a lot of photons in the same, in a small volume, and possibly on a small time scale, so on a small duration of the light pulse. This photon density is proportional to a quantity that is called spectral brightness or brilliance, which can be calculated either analytically or numerically. And this is the product of the spectral flux of photons times, actually divided by the volume defined by the intrinsic volume of the light pulse convoluted with the intrinsic volume of the massive particles emitting light, which are electrons, as I mentioned. Now, this quantity can be maximized under some specific conditions of the accelerator, which are summarized by this relation. Basically, the product of the spot size and angular divergence of your electron beam at the point of at the location where the radiation is emitted should be, which is called emittance, and we will use this term again in the following of this lecture. This emittance has to be smaller than the characteristic wavelength of radiation you want to use for your experiment. Now, if this condition is satisfied, you maximize the brightness. You are basically matching in phase space radiation and electron beam, and you get the maximum performance of your facility. And this condition is actually the one driving the race to fourth generation synchrotron light sources, which are now basically upgrading almost everywhere in the world to get to ultra low emittance and match the electron beams. Now, the gain in a large brilliance of the light pulse is actually not only in terms to maximize the photon density, as I said, but also because that also corresponds to a small denominator of the light pulse spot size and divergence. Now, which is basically can be translated into a well-collimated light pulse. Now, if the light pulse is well collimated, And during its transport through the beamline, you can minimize the footprint of the light pulse on the mirrors, on the optical objects, optical elements of your beamline, to either transport or manipulate the light pulse until reaching the sample. Now, if the footprint is small, that means you are also minimizing the sampling of the light pulse of errors which are intrinsic to the production, manufacturing of mirrors and optical elements in general. In other words, you are maximizing the transport efficiency of your beamline. The result is that the higher the brilliance is at the source where radiation is emitted in the accelerator, the higher the brilliance will be at the sample, just by virtue of an excellent transport. The development of storage ringlet sources in favor of light sources actually starts in the middle of the previous century, not with the first aim of producing radiation. These in the so-called first generation light sources, this emission of radiation was actually detected by chance, was not even predicted at the beginning and then elaborated from the theoretical point of view. The second generation light source, which is across the previous, the past and the present century, is developed with the aim of producing synchrotron light sources, light X-rays, basically parasitic to the operation of the synchrotron. And this generation saw the first dedicated facilities for the physics of matter. The third generation light source is the one running today, and now upgrading to a fourth generation, as I said, in order to maximize the brilliance by lowering the emittance of the electron beam. The sources, the magnetic sources of radiation emission are not only dipole magnets. There are, I mentioned already, different arrangements of small dipole magnets, which are called Wiggler or undulators, producing different features, both in terms of angular divergence, intensity, and coherence of radiation. And of course, the choice is basically of either one or the other source along the accelerator, is basically depending on the kind of experiment you want to carry on. I would like, now that the general picture, I hope, has been given, I would like to focus on one characteristic and maybe one of the most important parameters of a synchrotron light source, which is the electron beam energy. Now, the electron beam energy has a twofold balance in terms of design and performance of a synchrotron light source. The first point is that the photon energy that you have to have in mind in order to carry on your experiment is proportional to the cubic power of the electron beam energy. So this omega c, which is a characteristic frequency of your photon from a dipole magnet, is proportional to gamma cube of the electrons. Around the world, most of the third generation and the fourth generation synchrotron light sources can be classified in high energy, between around 6 and 8, up to 8 GeV electron beam energy, or below the 3 GeV beam energy. By virtue of this relationship, basically the two families are mainly driving science, exploiting soft X-rays for the low energy machines and hard X-rays for the high energy machines. But of course, there is an overlap, so that a 3 GeV machine can also produce a hard extender and the hard X-rays, maybe with a somehow reduced efficiency compared to a very high energy machine in the same spectral range. But still, I mean, these machines, the way we can produce light is has some flexibility, of course. The second point is that the centripetal force to which the particles are subject in a dipole is, of course, driven by the magnetic field, and this allows to extract a relation between the longitudinal momentum or energy of the particle and the curvature radius. Now, the technology allows us to implement some magnetic fields up to some value, let's say 2 Tesla for a dipole magnet, 4 Tesla or 6 Tesla for a superconducting dipole magnet. and around 1.2, 1.5 Tesla for an undulator. Now, said that, it means that the higher the electron beam energy, the larger should be the radius of the dipole and therefore of the circumference of the synchrotron. And this is actually reported here. If you look to the green line, you see a clear correlation between the circumference of existing third generation synchrotron light sources and the electron energy. There is also another curve, which is the blue line, which is saying that the emittance, the horizontal emittance in particular of these light sources is inversely proportional with some square root like law with the electron beam energy. And the reason is that the larger the circumference is, the more the knobs are to manipulate the electron beam in order to squeeze the emittance, as we will see now later on. Now, let me now enter a little bit more in the technical, in some technical details to introduce some technical ingredients to describe the dynamics, the transverse and longitudinal dynamics of particles in a synchrotron. Let's start with the fact that, as we said, particles are deviated in a dipole magnet. This is a top view of a dipole magnet. The magnetic field is entering into the plane. Particles with different energies by virtue of this previous relation, momentum and radius, are clearly subject to different radius, bending radius. So there is a separation that happens at the exit of the dipole magnet for two different energy particles. This separation, delta x, is typically normalized to the energy deviation, which gives us a parameter which we call an optical function. It's called a dispersion, which is a property of the lattice, of the magnetic lattice itself. So it has nothing to do with the kind of particles you are running the accelerator. It's a property of the magnetic lattice, or if you like, of the dipole magnet. So it's a matter to quantify, it's a manner to quantify the separation on the bending plane of particles at different energies. As you see from this picture, what you can imagine is that if particles have different energies, they're running over different lengths of their path, of their orbit, and this what we call momentum compaction. So the relative difference between the ratio of relative difference of path length and energy deviation. This quantity can be obviously, somehow naturally calculated through the knowledge of the dispersion function, which is something that you can imagine to compute with a tracking code, for example, if you are designing your accelerator. Now, this path length difference can be generalized to some time difference in arrival time at the exit of the dipole magnet, and we call this quantity the slip factor, which is again somehow proportional, almost identical to the momentum compaction, but with some low energy machines also perturbed by this 1 over gamma squared term. For very high energy, this term can be neglected because gamma is very large, and you basically end up with the same quantity in absolute value. Now, what is the relevance of this slip factor? Clearly, it's coupling longitudinal dynamics, the longitudinal momentum, and horizontal motion. So excursion in the bending plane, which is the horizontal one. And this enters into the determination of the longitudinal dynamics. Let's start from, let's make a step back. So we said that the particles in a synchrotron are emitting radiation, so they are losing energy, which means basically in order to get the energy constant, in order to get the reference photon energy constant over hours or days and so on, we need to replenish that energy. So we need some what we call accelerating cavities. There are objects that with a longitudinal electric field, which is varying with time and which is replenishing basically the electrons by the energy they lose by emitting radiation. Now, since particles arrive at the entrance of the cavity with slightly different times, just by virtue of the fact they are running on slightly different orbits, as we said before, there is a special phase, so a synchronism that we have to establish between the cavity field and the particles' arrival time in order to get the particles stored in the synchrotron in a stable way. In other words, the particles can arrive either later or earlier at the central cavity, where this deviation has to be small, but doing that over many, many turns, the motion will be stable if we can guarantee some oscillations around the reference particle, around the reference arrival time. This oscillation is clearly can be parameterized through an angular frequency of oscillation, which is written here. I don't want to enter into the explanation, physical explanation of all the details of this expression, but you see in yellow two highlighted parameters. One is the choice of the phase, CS, which has to be done in order to synchronize the cavity with the particles. And the second point is the slip factor. So depending on the sign of the slip factor and the synchronous phase, you have to make this argument of the root square of the square root, positive. So it's important to choose these two parameters in order to get stability in the longitudinal dynamics. And the stability, if achieved, is can be represented like closed orbits in the arrival time or phase coordinate versus the energy or relative energy deviation in the vertical on the vertical axis. So if you have stability, you have closed orbits in this phase space, which basically sets the amount of maximum energy deviation on the vertical plane and maximum time duration of your electron bunch in the synchrotron. These numbers are typically of the order of 0.1% for the energy deviation and typically tens of picoseconds in terms of electron bunch duration. And please notice that this time duration is actually reflects into the time duration of the light pulse that you are producing. Now, the fact that the electric field is oscillating in the cavity at a frequency which is much higher typically than the revolution frequency of the electrons in a synchrotron implies that each electron bunch actually that you can collect in a synchrotron relatively large number of electron bunches, and the number is just the ratio of the RF frequency, omega, and the revolution frequency. So this number, which is h, nothing to do with the Planck constant that I mentioned before. It's an integer large number, and it tells you how many bunches you can store in the synchrotron. They're typically of the order of several hundreds. So typical numbers of these longitudinal dynamics are 1 to few microseconds for hundreds up to kilometer long circumference. Each bunch is typically long tens of picoseconds, while the separation between the bunches is dictated by the radio frequency, is typically of the order of nanoseconds. So you are exploiting several orders of magnitude in time, starting from the single or few particle dynamics to the field pattern of the synchrotron. And typical numbers for synchrotron light sources are like this. So hundreds of milliamp stored average current with hundreds of bunches, thousands of hours of working time per year in with some time dedicated to machine operation and maintenance, and in order to satisfy the scientific requirement of thousands of users a year again. So these facilities are thought to be working every day, almost all year, along the whole year, on a calendar, with a calendar time, let's say, which is covers a big portion of the solar time of the calendar. So, there are specific field patterns which I want just to mention to let you know that in case some experiments don't require, or especially require, a single pulse emission instead of the emission from a train of bunches, you can arrange the field pattern so how to fill the synchrotron with electron bunches in order to isolate some bunches to let them running separately or together with the train, like sketched here. These kind of experiments are typically classified as a timing mode operation, and they're typically adopted in third generation synchronous sources. There will be fewer and fewer cases of these possibilities in fourth generation. Let's have a look to the magnetic lattice, which is basically the other important basically ingredient for building a synchrotron on top of course, an accelerating cavity. This is a snapshot of how a fourth generation synchrotron light source look like. This is inspired to the Elettra 2.0 project, which I'm participating to here in Trieste, now in upgrading phase. So you see in green the dipole magnets we have been talking about, and in between dipole magnets we have additional magnets. They are called multipoles. They are needed to force the electrons to basically to travel along the vacuum chamber, which is a tube made of a metallic tube, typically, where ultra low pressure is made in order to avoid the scattering between electrons and residual gas. And in other words, we need to focus these electrons along their path, and as long as they are stored in the synchrotron. Now, we are talking of magnets and not, for example, electrostatic devices, for a simple reason that from the technological point of view, it's much easier to manipulate high energy electrons with magnetic fields than electric fields. If you want to convince yourself of this, just calculate the ratio of for any given and equivalent force, purely electric and purely magnetic, to establish a focusing force on a particle. The ratio is basically the ratio of the electric field amplitude and the product of the velocity of the particle times the magnetic field. Now you end up with for the same force, you need, for example, 300 megawatt per meter electric field and equivalently 1 Tesla magnetic field. 1 Tesla can be easily manufactured at room temperature. 300 megawatt per meter is at the state of the art of accelerating cavities, so, and even not routinely achieved today. So there is no other way from the technical point of view of focusing electrons in the chamber, apart from using magnetic fields. On the right side, you have a snapshot of the section of a quadrupole magnet, which is a multiple made of 4 poles, where internal magnetic forces are established in order to focus particles of axis towards the center of the magnet, which is also presumably the center of the vacuum chamber. By simple satisfying the Maxwell equations, you can calculate how much is the focusing force, which is typically normalized to the particle momentum as function of the current ampere turns that you have to put in the coils to generate the magnetic field. So this K is the so-called normalized quadrupole strength, which is proportional, of course, to the magnetic field gradient that you generate between the poles. Now, for construction, a quadrupole is always generating a force which is focusing the electrons towards the center in one plane, but focusing them in the other plane. So there is no, by construction, because of Maxwell's equation, there is no way of focusing simultaneously the particle in both planes, which means that if you want to do that, and that's what we are aiming for with a series of quadrupole magnets, you have, as I said, you have to put focusing and defocusing magnets per plane, one after the other. In other words, a proper arrangement of strengths and the distances between the quadrupoles allow you to focus overall along the whole path, to focus simultaneously the particle in the horizontal and in the vertical plane. If you like, this top plot is a top view of the particle trajectory along a series of quadrupoles, and the bottom plot is a lateral view of the particle trajectory along the same quadrupoles. So as long as you keep the particles within the chamber, you are ensuring somehow transverse stability. The fact the particles are oscillating, as you see here, in X and Y coordinate, suggests us that we can describe the transverse dynamics with a pseudo-harmonic oscillator. What do I mean? Where something which is proportional, so something where we can describe the particle position and its angular divergence as an amplitude times an oscillating term. We have here several mathematical notations. We have beta and alpha, which are determining the amplitude of oscillation, delta mu, which is the relative phase advance, which can be inferred from the knowledge of the amplitudes. And we have an additional term, which is J, where U stands for X or Y. J is a constant of proportionality, if you like, which has nevertheless a physical meaning, a geometric meaning. Now, if we represent in the phase space U and U prime such harmonic oscillation, we get an ellipse, it's relatively easy to demonstrate that by combining these two equations, you can get the equation of an ellipse in the phase space UU prime. Now, each particle is basically oscillating according to this simplification of the motion, is moving along one orbit, so along one ellipse. The fact is that as long as the motion is linear, so as long as we are implementing dipole and quadrupole magnets only, and we have no additional frictional forces, so the system is approximated to a non-dissipative one, the area of the ellipse, whatever the ellipse does, whatever the ellipse will be along the accelerator, the area will be constant. This applies to each particle, and of course, naturally, it applies to an ensemble of particles. So what accelerator physicists do typically is to represent the distribution of particles in the phase space by superimposing or representing it through a simplification, which is an ellipse, as you see here, an ellipse containing most or a given percentage of your charge. The area of this ellipse is what we call the emittance already. So it's because for a normal ellipse, so for a properly oriented ellipse, we can calculate its area like the product of the semi-axes, which are nothing else the spot size and the angular divergence of the charge distribution. So this emittance is, under given assumptions, a constant of the motion. The other important parameter is the beta-tron tune. In other words, the number of oscillations the particles do over a turn by virtue of the quadrupole focusing. And as I mentioned already, this quantity can be calculated from the knowledge of the amplitude of oscillation, which can be in turn computed numerically through codes once the magnetic lattice is known. Now, this quantity is also important because it tells us how frequent are the oscillations, so how along a turn, and as we'll see in a moment, it has to do with some perturbations to the motion, which are due to unavoidable errors in building up an accelerator. Now, the point, and I will stop here before making a break, let's recall the importance of this beta-tron tune parameter and to associate it to the typical perturbations in a synchrotron light source. Now, we said that particles are focused by a quadrupole magnet, right? But as it happens in a dipole, where different energy particles with different particles of different energy are bent by differently from the same magnetic field, the same happens in a quadrupole, which acts like a dipole on a much shorter scale. In other words, particles with different longitudinal momentum or different energy will be focused differently from the same quadrupole field gradient. Now, this means that basically these particles will be oscillating slightly different one from another. These particles belong to the same bunch even, okay? So in a same packet same bunch of electrons, we have basically all electrons as oscillating slightly differently one from another. This difference implies a different beta-tron tune, different number of oscillations per turn. And this difference is, of course, related to the energy deviation. So we are used to parameterize this deviation in focusing property as the so-called linear chromaticity, the ratio of the tune shift, so the discrepancy in beta-tron tune, one particle from another, normalized to the standard, to the RMS energy deviation. It can be shown that this quantity is actually, again, a property of the lattice. It has nothing to do, as we did we mentioned for the dispersion before. So it has nothing to do with the nature of the particles. It's a characteristic of the magnetic lattice. Once you define a magnetic lattice, so a given sequence of quadrupoles, you are defining strengths and beta-tron functions, which are amplitude of oscillations. And the product determines the linear chromaticity. This number can be large, which means that for any small energy deviation, the beta-tron tune deviation of the particles can be large compared to the nominal working point, to the nominal beta-tron tune you are designing the synchrotron for. What is the issue with a deviation, with a tune shift, with a beta-tron tune shift? Now, the problem is the following. Once you build the synchrotron, you imagine to identify your working point, so to have all particles oscillating with a horizontal and a vertical Betatron tunes, which are represented in this diagram. All these lines represent relations between the tunes and integer numbers. Now, let's assume we have a perturbation of the orbit along the synchrotron, which can be due, for example, to a misaligned quadrupole, a misaligned dipole, or mispowered dipole magnet. So basically an error on the magnetic field of either a quadrupole or a dipole or a series of magnets and so on. You are basically perturbing the nominal orbit. And doing this, if the particle goes back to the perturbation always with the same position and angular divergence, the perturbation starts resonating with the orbit of the particle. In other words, you are amplifying the error, the effect of the error on the orbit of the particle, and that perturbation can lead to an amplification of the orbit deviation, which means basically at the end, after many turns, the particle can get lost. Now, this resonant amplification suggests a relation between the tune of the particle, so how many oscillations it does per turn, and the driving force of the perturbation. In other words, we have to avoid all those conditions in which tunes are related to integer numbers, which are the solid and dashed lines in this diagram, and to put our working point, so in other words, we have to design our synchrotron in a way that our nominal Betatron tunes sit on an empty region in this diagram. This way, in the presence of any arbitrarily strong perturbation, we should be safe enough from an amplification of the perturbation effect. Once we do this, however, the linear chromaticity naturally shifts the design working point by virtue of the fact that the particles intrinsically have spreading longitudinal momentum. We have seen that it's coming directly from the fact that we have to accelerate them, and all particles are arriving at the cavity at slightly different times. So this delta is an avoidable parameter of our synchrotron, of our synchronous accelerator. So this implies that the chromaticity is an unavoidable effect of our dynamics. And that means that whatsoever the nominal working point will be, it will be shifted by linear chromaticity. So the next step is to arrange magnets in order to get this chromaticity corrected, ideally to 0 or to any arbitrary number that we like, in order to minimize the Betatron tune shift. So in order to avoid sampling these resonance lines. How to do that? Well, as you see from the top expression, if you add more and stronger quadruples, you are just amplifying the chromaticity. That's not the way we want to do, the way we want to go for. The next step is to use higher multiple magnets, for example, sextuplets, which act like equivalent quadruples, but without introducing an additional K. They are capable basically of minimizing this natural chromaticity by adding terms to this expression. And by adding terms, you can cancel out somehow the overall result. The drawback of adding higher multiple magnets is the fact that they're not only working in favor of stability in the transverse plane, but they're also adding so-called geometric aberrations. In other words, they're adding additional distortions to the linear orbit that we assumed at the beginning. Now, the strength of the sextuple is inversely proportional to the strength of the dispersion that we generated with the dipoles. The stronger the dipole field, the larger is the separation of particles in the bending plane, the larger is the dispersion, which means that the larger the number of dipole magnets is, the smaller the dispersion is, the stronger the sextuple field should be. So the final aim is to have sextuples with the lowest sextuple strength as possible in order to minimize aberrations, which means that in a lattice where you have a few dipole magnets in a circumference, this dispersion is large, the number of dipoles is small, so the sextuple strength is small. They work efficiently without inducing much of aberrations. If we have many dipoles in a circumference, the opposite is true. So we have large NB, which means that for the same correction of chromaticity, you need strong sextuple magnets. And this implies additional perturbations in terms of nonlinear dynamics to the stability of the electrons. I will just stop here since we already introduced many different concepts, and I would ask if there are questions before making a break, maybe.
Okay, so I don't see any questions from the chat. If you have some question, please digit on the chat because I cannot see all the, if you raise your hand, it's very difficult to see that because you are many. So please, if you have questions for Simone, write quickly in the chat and I can read it.
And please don't be shy if you have curiosity also from the basic point of view. And you want I repeat something or maybe go back to some of the concepts, feel free to ask.
There is one question. So it's a question from Zuo-kun Zhang. I hope I pronounced correctly. So in one of the slides, you mentioned 6D electron. What are the extra 3D sites besides X, Y, and Z? I repeat the question. In one of the slides, you mentioned 6D electrons. What are the extra 3D besides X, Y, and Z?
I think I was referring to a 6D photon density here, which of course implies a 6D charge density. So I hope this is the slide you're referring to, and thank you for the question. So the 6D is referring to horizontal, if you are referring to light for the moment, which is, and that's what the brilliance parameter is referring to. So it's a density of photons in horizontal position, horizontal divergence, vertical position, vertical divergence, longitudinal position or time coordinate, and the frequency, which is also equivalent for a photon to photon energy. So these are the 6 parameters identifying a 6D volume of the light pulse. Of course, as I said, this is intrinsically related to the charge density of the electrons. Okay, the higher the electron density is, the higher the photon density is, roughly speaking. So also for electrons, we have to manage the electron bunch in order to get relatively small horizontal and position and divergence, or spot size and divergence for a beam, small vertical spot size and divergence, possibly small time duration, and a relatively small energy spread or momentum spread for the electrons. So that's the 6D volume I was referring to. We typically, for electrons, what we can typically manage is the horizontal phase space, because by manipulating magnets, and as we will see in a moment, we could, by arranging magnets in a proper way, we can basically manipulate the horizontal emittance. The vertical emittance is typically a small fraction of the horizontal one and only determined by residual errors in assembling the magnets, as expressed here. So there is an empirical factor which is typically of the order of 1 per mil. For the duration and energy spread of the electrons, instead, we rely on the longitudinal dynamics that I was describing here. And these numbers cannot be manipulated strongly, basically. So these ranges are basically fixed, apart from very advanced schemes on bunch length manipulation that I'm not going to discuss in this lecture.
There are other questions. One very basic one, but I think it's worth to reply to this because you will mention. What do you mean by lattice?
Yes, correct. That's a good point. And I'm sorry for not being exhaustive enough to that what in jargon The lattice is a series of magnetic elements. Am I sharing? Yes, I think I'm still sharing.
Yes,
so
yes.
I'm referring to the sequence of dipole and quadrupole and possibly sextupole magnets in a synchrotron. That's the lattice.
Very, very good. Thank you. And there are another interesting question is from Zakaria Abd El Fattah. Can synchrotron rings facility made smaller or compact in the laboratory scale in the near future, maintaining the brightness and coherence?
Okay, that's a good and very interesting question.
Yes.
Unfortunately, this plot suggests that if you want very high energy, not only high energy of the photons, but also high intensity, there is no way to squeeze a synchrotron to size of a cyclotron, for example, which has only a few meters of bending radius. So as far as I know, no way of doing it. But you can produce X-rays still collimated in a very high energy, but much lower intensity, for example, with a linear accelerator, or even in a very compact circular synchrotron, which is based on Compton scattering. So it's another way of doing radiation, making radiation not through magnetic elements, but by hitting an external laser with accelerated electrons, and the backscattered photons will be boosted in energy, so that you can easily get X-rays and even gamma rays. These facilities, for example, compact Compton ring exists already. It's produced by the Linsen company, as far as I know. It's used in Germany at least. And linear Compton sources are also spread around the world.
Thank you. And there is somebody that would like to visit Elettra. Maybe Simone, you can.
Absolutely, with great pleasure. Feel free. I think in each of the slides is my email address. Just write to me an email, please. We'll arrange somehow. Maybe depending, we'll arrange a schedule at least.
Probably after the upgrade.
Yeah.
But probably after the upgrade.
Most likely, yes. Which will be.
As far as I know now, it's quite messy inside the experimental hall.
Absolutely. We have dismounted already Elettra, and Elettra 2.0 is going to be installed. So we'll be warming up the machine at the end, fortunately, likely at the end of this year. But please feel free to write to me.
Okay, so other questions, I would like to read them. One is which beam dynamic codes is most suitable for synchrotron, including the non-linear dynamic studies?
Okay, I would suggest Elegant, which is a free code made in US and quite well developed these times. But there are many others like OPA, MAD is developed mainly at CERN now. I'm particularly familiar with Elegant. It's a very powerful tool, although sometimes not very user-friendly. But once you are in, and there is a forum supporting all doubts, it's a 20 years old code now.
Other small question, can you say something on damping using Robinson wigglers and how it's influenced the bunch length?
We'll see that in a moment. So I will postpone
Very
to
good.
The next second part.
Yes, and how could we correct spherical aberration of the beam? What type of magnets to be used? This is also...
Well, when we are talking of aberrations, basically the way we are going to correct them is either to cancel aberrations generated by different sextuples through a proper arrangement of sextuples in the lattice. So you can choose strengths and positions of the sextuples in order to cancel out somehow to make a destructive interference of these aberrations, or so as a complementary solution to add higher multiple magnets, for example, octuples and decuples. Octuples are now systematically included in fourth generation synchrotron light sources.
Thank you, Simone. There are the two last questions for this first part, and then we make a little break. So, so there is somebody that wants to know. Let me understand the question. I want to find out with the magnetic field, is the distance between the field structure the same, or they are variable from one field to another field? It's difficult.
Are you referring to the difficult to understand if well, I don't know. Let's try to answer. When we are talking of magnets, we typically sketch them as this is in this slide. This is a sorry. Where is it? This is a section. So the particles are entering into the on your screen, into the screen, and you have an ideal particle is traveling along the symmetric axis of this geometry, right? At the very center of this symmetric geometry. Forces are non-zero as the particles are slightly out of the central of the magnet in any direction. Okay. So, and in particular, the force is made to be such that it's stronger in value in proportion to the offset of the particles from the center. So that's the restoring capability of the magnetic force of quadrupoles. So we are defining forces basically slightly off the axis in a region which is occupied by the beam. And if instead you were referring to accelerating field, what happens in a cavity is that the accelerating longitudinal electric field is right on the axis of the cavity, which is also where the beam is passing through. Off axis, you still have some accelerating field, but typically the beam is has a transverse dimension of the order of hundreds down to few microns, with offsets of the order of 100 micron. In other words, the region where the longitudinal electric field is accelerating is pretty small, and that's where you want to get the field you design the cavity for. Out or far from this axis, there is nothing basically in terms of accelerating field. And I hope I answered the question, although I'm not sure.
I mean, there are now there are a lot of questions coming.
Okay.
I just want to. There are some questions that are more basic than others. So I want to read just the basic questions, and please reply quite straightforward. For the more specialized questions, we don't have time. So I encourage you to contact Simone directly because some questions are really articulated and maybe it's for less interest for a lot of people. But there are a couple of questions that I think it's useful to reply. It's one, why the synchrotron radiation more significant for electrons than for protons? This I think everybody should understand this. And also why in any synchrotron, this is the example of Shanghai synchrotron, every 12 hours they have to stop and they have to do some energy raising for correction. Sure. I mean, these are the last two questions for this first part. More complicated questions, please contact directly Simone.
So first question, it's very important. I will repeat it because I went very fast on this. So the power of synchrotron radiation emitted in a dipole magnet, but this applies to any arrangement of dipole magnets, so even in an undulator, is inversely proportional to the rest mass of the particle. This is an invariant of the particle. So for any particle species, you have a given quantity, which is m0. And this is, by the way, at the fourth power at the denominator. So a proton has typically 2000 heavier rest mass than an electron. That means that the lighter the particle is, so the smaller m0 is, the larger the power of synchrotron radiation emitted will be for the same particle energy and the same magnetic field. That's why we don't accelerate protons typically to emit radiation, because they are not very efficient emitter of synchrotron radiation for the same total energy and the same magnetic field, right? And that's why we use electrons instead, which are the lighter massive particles we know. And the second question was about why they have to stop. We will see it again in a moment, but typically because there are different ways of operating a synchrotron. The beam has a given lifetime, so the current stored in a synchrotron is going to change over time, and time to time you have to replenish the synchrotron with a given amount of charge to go back to the nominal current level. I will mention it in the second part.
Okay, thank you. I think we should do a small break of 5 minutes. I mean, it's 1:56. We can restart at 2:01, sorry.
Yeah.
So Simone, with Simone Di Mitri from Elettra Syncrotrone Trieste, that he will continue his lecture on design and operation of accelerator, chain, and storage ring.
Yeah, so back to sharing my slides. Here they are, and now display mode. So we introduced some nonlinear perturbation to the transverse dynamics of particles. We are now going to look to the motion of the beam particles as an ensemble, and in particular referring to the so-called process of damping and the equilibrium distribution. Now, I mentioned the fact that the particles are emitting radiation. The simplified picture is that each photon, which is the smallest quantity you can use to define an electromagnetic field, and we can describe equivalently as a particle. The simplified picture, I was saying, it assumes the photon is emitted instantaneously along the direction the electron is moving at the point of emission. In reality, these photons are distributed in space and therefore in angle, in the horizontal and in the vertical plane. And the fact, by conservation of momenta, there is a back scattering, if you like, of the electron as the photon is emitted, also in the horizontal as well in the vertical plane. In other words, the emission of radiation implies a perturbation of the electron orbit that basically tends to add a contribution, a positive contribution to the size and angular divergence of the electron distribution. This effect is called quantum excitation, and is basically the process giving rise to an excitation or enlargement of the electron beam emittance. At the same time, as the electrons are emitting radiation, we have to replenish that energy with an accelerating cavity, which is, again, a quite simplified picture, but still, realistic to our purposes. It's an object which is increasing the longitudinal momentum of the particle while keeping the transverse momentum untouched. This means that the angular divergence of the particle, which is nothing else x prime, which is nothing else the ratio of the transverse and longitudinal momentum, will be reduced by longitudinal acceleration. This process is called damping, radiation damping, as a consequence of the fact that because of radiation emission, we need to keep the particle energy constant, anyhow, on average in a turn. So this reduction in divergence is actually contributing to a reduction of the emittance, in this case in the horizontal plane, which is, I recall here, a product of beam size and beam divergence. So the two processes, the quantum excitation and the radiation damping process, happen simultaneously, and their interaction can be described mathematically as a sequence of, by investigating, if you like, the variation, the average variation in a bunch of the amplitude of oscillation over a time interval, which is basically one turn. Now, this quantity sees the contribution of both processes, which can be exemplified in this expression below as the one with a negative sign and the one with a positive sign. Now, clearly, the two quantities can be made overall zero. And in other words, there is one solution which describes null variation of the amplitude of oscillation in the presence of radiation emission and longitudinal acceleration. This solution is actually describing the equilibrium of the charge distribution in the presence of all these processes. And the mathematical expression puts in evidence two kind of quantities. The first one is a time interval, which is proportional to the revolution period, let's say 1 microsecond, times the particle energy divided by the amount of energy the particle radiates in a turn. This ratio, E0 divided by U0, is typically a large number because U0 is much smaller, let's say 1 per mil of E0. Now, that means that the so-called the damping time in something which is basically something of the order of 1000 turns, which sets the time scale on which the equilibrium is reached. The second expression, the second contribution highlights this Hx function and the amount of synchrotron radiation power emitted. So this Hx is proportional to the dispersion function. I remind you, the dispersion is proportional to basically the bending angle in a dipole magnet, and therefore inversely proportional to the number of dipoles in a synchrotron. The larger the dispersion is, the larger the amount of radiation is, the easier is the way you can counteract the quantum excitation. In other words, by combining these two terms, you always get to an equilibrium condition, which translates into an equilibrium emittance, which is another way of parameterizing the horizontal distribution in the x prime phase space. Now, I'm giving you here, without derivation, the behavior of emittance when the beam is injected. Please follow the red line here in this plot. Once the beam is injected in a synchrotron at any, let's say, somehow arbitrary value, it depends on how the beam is generated and accelerated up to the synchrotron energy. We'll see in a moment how this chain of accelerators is built. Anyhow, for any given value, the emittance sooner or later will go back to the equilibrium value, which is independent from the initial conditions. And this equilibrium, as I said, is contributed by a radiation damping process, which is going to minimize the emittance, and the quantum excitation, which is going to excite it, to enlarge it. An analytical expression for the equilibrium emittance can be given, and the physical quantities you have to keep in mind to follow somehow these dynamics are the square, the gamma. So the equilibrium emittance is larger for larger electron beam energy with a power of 2, and inversely proportional to the number of dipoles, NB, to the cube, which means that for the same circumference and the same electron beam energy, by enlarging the number of dipole magnets, in other words, by splitting your dipole in many, many pieces, if you like, you can minimize the emittance by quite a large number. And that's what the fourth generation synchrotron light sources are doing. They're just keeping almost the same beam energy, the same circumference, so the same vacuum chamber, if you like, but splitting the dipole magnets around the chamber and putting them to a large number. By reducing the horizontal emittance, as we saw in the very first slides, we are maximizing the brilliance or spectral brightness of emitting radiation, of the emitted radiation, which basically means we are maximizing the photon density and therefore improving the performance of our synchrotron light source. Now, there are several considerations, if you are familiar with Hamiltonian dynamics, that can be brought to your attention in order to justify such a description of emittance through an analytical expression. But I want just to give you this message. The synchrotron is not per se a Hamiltonian system. In other words, it's not conservative. In other words, there are time varying fields which are not conservative. Is not a linear system because we saw, for example, we include sextuple or even octuple magnets to correct the transverse dynamic stability and so on. In spite of this, we combine all these objects and simplify our description of the particles motion in a synchrotron in order to be behaving like a Hamiltonian system. So we typically, if the synchrotron is designed properly, then we can describe it as an approximate, conservative, and linear system. And that's why we can somehow manipulate the charge distribution according to our specifications, okay? So we have to keep all the accelerator parameters in a given range in order to be these approximations satisfied. This is one of the main tasks of an accelerator designer, if you like. Now, I mentioned these fourth generation synchrotron light sources. They are also called diffraction limited storage rings because by reducing the emittance of the electron beam, you are satisfying the relationship that I showed you before with the wavelength of emitted radiation, which is the so-called diffraction limit. So we are passing from relatively sparse magnetic lattice. This is a picture of a snapshot of the Elettra achromat, let's say a portion of the Elettra magnetic lattice before it was dismounted a few months ago, passing to what will be Elettra 2.0 with a much more dense, strong focusing lattices. This kind of development, so by adding more dipole magnets and which imply basically a stronger focusing property in order to keep the electrons on the reference orbit, has inspired engineers and physicists to the design of very special dipole quadrupole magnets, combined magnets, take into account all different field maps, interference, and of fields, magnetic fields from one magnet to the other, and so on. And this is a business per se, so it's a real job, the one of magnetic design, I mean, which has, of course, continuous interaction with the physics of the electron beam. This gives you again a picture of worldwide of the emittance, equilibrium emittance at different synchrotron light sources as function of the circumference of the light source, which is also proportional, as I mentioned in the first part, to the photon energy. The blue line is representing a fit of the experimental points of third generation synchrotron light sources. As the number of dipoles have been increased, or will be increased in the near future, we move from the blue line to the red and green lines. And this gap, so this reduction in equilibrium emittance, here normalized to the electron beam energy, but it doesn't really matter. So this reduction in emittance is basically due, mainly due to the magnets technology. So as a consequence of reduction in emittance, as I said, we are going to reduce the spot size and so the beam size and the beam divergence of the electrons, and consequently the spot size and divergence of the photon beam emitted by the electron bunches. And this is the difference that you can get typically 1 to 2 orders of magnitude in sizes of the light pulse, passing from the third to the fourth generation. I mentioned other ways of producing radiation on top of dipoles, which are undulators. So an undulator, in the most simplified picture, is a sequence of small dipole magnets. The full scale of the length of each dipole, in this case, is a centimeter scale instead of a meter. And then you put all these small periods with opposite or alternated sign of dipole field in a sequence to build a 1 meter device, which is the undulator. So the electrons are basically wiggling into the undulator by virtue of alternated polarity of these small dipoles. By doing this, radiation is emitted at each pole, or each period, if you like, of the undulator. The constructive interference of this radiation emitted along all these periods, which are typically in a large number, say up to several tens to hundreds, radiation is characterized by a very central frequency, so a relatively narrow bandwidth. In other words, most of the radiation is emitted at a given wavelength, which is a function of the undulator period, inversely proportional to the square of the particle energy, plus some correcting factors which depend on K, which is the proportional to the strength of the magnetic field, of course, and the angle observation theta. Now, there are different techniques and technologies actually to build an undulator. You will hear more today about that, but just to mention normal, so room temperature compact undulators, cryogenic undulators, superconducting undulators, or even high temperature superconducting undulators. So different technologies allow you to reach different field strength, different periods, and therefore to reach out different wavelength range, trying to basically save money in terms of lower electron beam energies and profiting of the smaller size of the electron beams in a fourth generation synchrotron light source. So the next generation of undulators are aiming for shorter periods and stronger fields. The shorter period is driving the race to shorter and shorter wavelengths at relatively high intensity, while basically allowing the electron beam energy to be consequently lowered, implying some cost saving. Now, fourth generation solar ring light sources are already running. The first one in Sweden already years ago, actually. The second one recently in Grenoble in France, and very recently in Switzerland. I forgot the second one actually was the one in Brazil. Last year in US. Few others are coming in Asia, China and Korea, in Italy, Elettra 2. There is a project running in California, and few others are already in the design stage in the UK, Germany, France. France I mentioned already, and there is one actually in the Paris area and in Spain. So let's after this overview, let's go back to a few additional ingredients describing the dynamics of along the full undulator, the full accelerator chain in such an infrastructure. So far we have been focusing our attention to the synchrotron, but the synchrotron is not the only object that is part of a research infrastructure like a light source. Let's start from the fact that, as some of you mentioned by putting a question about that, let's start from the fact that, as a matter of fact, the amount of charge that we inject in a synchrotron is not constant over time. It's almost constant, but not really. Since the distribution tends to be a Gaussian in the transverse as well as in the longitudinal phase space, but in particular in the transverse, the Gaussian tails of this charge distribution hit the chamber, the vacuum chamber wall, which means that slightly and slowly we are basically losing particles on the vacuum chamber. In other words, we are cutting the tails of this Gaussian. So this charge loss can either be quite a linear, let's say smooth process, or driven by nonlinearities in the transverse dynamics, like those driven by strong sextupole or higher order multiples and field errors. So of course, a pure linear machine, as far as the transverse dynamics is our target, is our ideal condition, but nonlinearities are basically part of our life every day, and we have to manage them. They contribute to this to the reduction of the lifetime of the current stored in a synchrotron, and we can characterize this lifetime in several ways. But what I'm more interested here into is the fact that once you inject the current, and please look to the bottom right plot here, once you inject a given current into the synchrotron, because of this charge loss, typically, of course, unwanted, you are basically reducing the stored current over time until you reach a point where the current is no longer enough to satisfy users in terms of photon intensity, because the amount of power is, of course, synchrotron radiation power is proportional to the number of electrons which are stored in a synchrotron. So you have to reinject an amount of charge by filling up several bunches until you go back to this nominal maximum stored current and so on. This decay mode was typical of second and third generation synchrotron light sources until top-up injection was demonstrated. In other words, top-up or top-off injection is nothing else a very frequent injection before the current goes down by a large amount. This way, every, let's say, 5 minutes, you inject a very small amount of charge in order to keep the total current constant. Of course, in order to do this, the lifetime of your beam has to be long enough to be compatible with every few minutes new injection. But this is what happens in most recent and the next fourth generation synchrotron light sources, and this has two advantages. One is that the current level and therefore the intensity of emitted radiation is constant over time. This is very typically appreciated by users. And the second point is that the thermal load due to radiation hitting the chamber remains constant over time, which implies a far better mechanical stability of all the components of your accelerator over time. Now, how to inject frequently, or every given time into the synchrotron? That's done through a chain of accelerators, like the one shown here. Typically, a synchrotron light source facility is built like this. So you have a, let's say, what is called a thermoionic gun. So if you can imagine like a metallic source, a cathode, from which you extract electrons by rising the temperature of the cathode to very high values. For example, tungsten or something else. This electron cloud is injected into a small linear accelerator, which is made of the accelerating cavities I've been mentioning before. This is bringing electrons typically to the level of 100 MeV kinetic or total energy. Then these electrons are injected into a small synchrotron. This is a synchrotron with a simplified magnetic lattice. It's not aiming to produce radiation or high quality radiation, but just to ramp the electron beam energy up to the target energy of the main ring. So this is called the booster ring. And once the target energy is reached over many turns, the booster ring is injecting the electrons into the main ring, which is the synchrotron properly said. So we call this the injection chain into the storage ring light source. And of course, all these accelerators, the linear, the booster, the main ring, are connected by transfer lines. In other words, a series of dipole and quadrupole magnets to connect the different accelerators at a constant energy. These are pictures giving you a taste, let's say, of how a linear accelerator looks like, if you haven't seen it before. This is a picture of the Elettra booster ring. You see many long dipoles with very few quadruples in a purely periodic lattice. And here you have a snapshot of another important issue, which is concerning injection, which is, of course, the synchronization between arrival time, accelerating part, and accelerating field in the LINAC, in the booster ring, and in the main ring. So you see here in the picture, you have some yellow blocks, which represent, if you like, electron bunches. They are generated in the LINAC. Let's see it again. Accelerated, injected into the booster. After several turns, they reach the nominal energy, and they're injected in the synchrotron there, where they will be stored for many hours and possibly days. The connection between the LINAC and the booster and the main ring is made of dipole magnets, which are used to deviate the orbit, the trajectory of these bunches in order to be extracted from one accelerator, injected into the next one. And this is quite a delicate and complicated piece of the facility, how it is sketched here, which implies a sequence of pulsed magnetic elements, DC magnetic elements, electric elements, and shielding, metallic shielding, in order not to make the electric fields interfering and the magnetic field interfering one to another. Anyhow, this is just to illustrate, I mean, some of the critical issues in designing an accelerator chain, which implies the knowledge of beam physics and technology in linear and circular accelerators on top of diagnostics, synchronization, computing resources, and so on. Other facilities, few ones in the world at the moment, are actually using very long high-energy electron LINACs to inject into the main ring instead of passing through a booster one. This happens in Sweden at the Max IV laboratory, in Japan at the SAC-LA, and in South Korea at the Pohang Accelerator Laboratory. Such a long LINAC brings the electrons directly to the target energy. At that energy, the electrons are injected into the main ring directly. And this long LINAC, in all the two cases in Asia, I mentioned here, is used also to produce other kind of radiation, which is that one of a free electron laser, which is another kind of object I'm not discussing today. In the Max IV case, instead, there was a plan to make a free electron laser with a long LINAC, but so far they have been producing just short light pulses at the level of a sub-picosecond time scale. So this is another way and far more efficient in order to inject electrons, bringing electrons from low energy to high energy and finally injecting into the main ring. But of course, as you may imagine, the cost of building such a very long high energy LINAC is typically factors higher than building a booster chain. And I'm now basically at the conclusions quite far in advance compared to my schedule, but this maybe will give us some more time, give you some more time to put questions. I would like to give you, I mean, you bring home the following messages talking of synchrotron light sources and advanced light sources in general. Now, you have to keep in mind that accelerator-based light sources, which are implying, as you maybe have understood, a large infrastructure, so many resources, both in terms of money and people and technology, are the most brilliant sources on Earth. In other words, you cannot, at the moment, we are not capable of producing radiation as collimated as it is in a synchrotron light source, for example, with the same intensity in the X-ray wavelength range. This kind of radiation is not only very brilliant, so with a high density, but also largely coherent. In synchrotron light sources, and especially the fourth generation, this transverse coherence is basically a property which allows a far more efficient interaction of light with matter once the photons hit the sample. So for any given number of photons, if the number of photons of coherent photons is large, it means you are basically using all those photons to establish a process in your sample. Free electron lasers, which I mentioned also, are sources which not only guarantee transverse, but also longitudinal coherence. One of the strongest points of synchrotron light sources is the fact that they're extremely flexible in providing control of light polarization, which is, if you are not familiar, I'm not sure how familiar you are with this term, but it's basically describing the plane in which the electric field or magnetic field associated to an electromagnetic wave is oscillating. And this has to do with different kind of processes that you can drive in your sample. So this polarization can be manipulated from linear, horizontal, vertical, circular, elliptical, and so on in a different series of states by manipulating basically the geometry of your undulator, for example. Not really acting on the electrons, but basically acting on the undulator geometry, for example, by moving the arrays of dipole magnets in order to establish different orbits in the undulator itself, and therefore allow the electrons to generate different polarization states of radiation. The repetition rate is also a number which is typically very large in a synchrotron. You might remind I mentioned a microsecond or so revolution period, which means the typical single bunch emission has a natural frequency of 1 megahertz in a synchrotron. And if you have 400 bunches, for example, that means that the full train of bunches are emitting at a repetition rate of 400 megahertz, while linear accelerators are nowadays targeting 1 megahertz repetition rate and still to be demonstrated. So that means you are collecting a number of photons at very high frequency, okay? The light sources are, of course, driving technology, which can and is also used somewhere else in radio frequency, magnetic technology, ultra vacuum mechanics, and in some cases lasers, which are complementary tools to excite processes on a sample and to be probed with a synchrotron radiation. And they are typically multi-purpose science drivers, which means that there is no one ideal source, not only between synchrotron and FELs or Compton sources, which I mentioned too, but basically once you have a given experiment in mind, you have to look for the specific light source which is the most suited, the better suited for your experiment. And among the synchrotrons, there are of course differences because of the electron beam energy of the undulators or the geometry of the beamlines that can exploit different radiation properties. So you have basically to look for your ideal source. The strong points of synchrotron light sources are not only limited to the quality of radiation, but also on their capability of providing light simultaneously and continuously, basically over the year, to tens of beamlines simultaneously. So that means by virtue of the circular geometry, this light is emitted at every turning point along the circumference, at any dipole, at any undulator, all the time. That means by connecting one photon beamline to the source point, you are receiving light all the time, okay? But since each beamline is basically providing light to a different experimental chamber, that means you are basically making many different experiments at the same time from the same facility, from the same, let's say, in the same facility, okay? By virtue of the periodic motion on a circular orbit, the emission of radiation is also extremely stable, especially if compared to a linear accelerator and therefore a linear-based light source like a free electron laser. This stability concerns not only the intensity. The top-up injection is one of the main ingredients allowing for a stable intensity of emitted radiation, but also in position and divergence. And the next generation, the fourth generation of synchronous light sources are now targeting the transverse coherence, a high degree of transverse coherence in tender and even hard X-rays, which has never been demonstrated yet at such kind of facilities. So the promises of diffraction limited storage rings, as the fourth generation is called, is that one of improving the capability of experimentalists basically in carrying on their studies, not only by improving the efficiency of light matter interaction, which can imply a reduction in time, in acquisition time, for example, of data due to this light matter interaction, but also in order to allow new experiments exploiting, for example, higher intensity at a given spectral range, and or in exploiting higher lateral resolution, which is a natural consequence of transverse coherence. So typically, the experimental techniques which are gaining more from the fourth generation are related, those ones implementing coherent diffraction imaging, tachography, which is another way of processing basically diffraction imaging results, and X-ray photon correlation spectroscopy. But again, spectroscopy is also another way we are basically, another technique is gaining from this kind of sources in a less obvious way. Now, what the future looks like is probably almost known at this stage. It's probably not known what is going to happen in a decade or so, as it was not a decade ago. So this is a picture of the Elettra laboratory. You are very welcome to visit us and to see what are the plans for the synchrotron, and moving from Elettra to Elettra 2.0, and maybe if you get a chance to visit also our linear accelerator, where we are managing also a free electron laser. As I said, what the future looks like is not known yet, but any better idea or good idea for future developments is welcome all the time. I'm putting here some references for your convenience. I invite you to, and many of them, the first two are basically free online. And then a series of technical papers to which I inspired and from which I grabbed pictures. So which I invite you in case you want to deepen some of the topics which I've been discussing today. And with this, I thank you for your attention, and I'm open to questions.
Thank you, Simone, for this very in-depth presentation. And I think we have time for some questions. The first question is about coherence, actually. That was, can you tell us about the comparison between the coherence in the synchrotron light source of fourth generation, so diffraction limited, and the coherence of a free electron laser of an XFEL?
Yeah, I have a picture which could be useful to this purpose. So this is actually a slide trying to define coherence. Let's focus our attention on transverse coherence, as I think it was put in the question. So the capability of the light of satisfying a given relation in terms of, let's say, position and transverse momentum of the photons. Again, coherence, let's define coherence in this context like a correlation that can be established in the transverse plane between position and so phase and momentum energy or momentum or energy of the photon. As far as the diffraction limit is satisfied, the diffraction limit is satisfied by the electrons, which are the sources of radiation emission, and a given wavelength at which we want to consider the emitted radiation. The coherence is guaranteed naturally, either if it is a linear or a circular accelerator providing the electrons. So in that sense, once the physical parameters of the light pulse, the wavelength, and the electrons, the emittance, are correlated according to the diffraction limit, we are exploiting actually exactly the same physics. The fourth generation of synchrotron light sources are going to guarantee a degree of coherence at a given wavelength. So it doesn't make any sense to specify a diffraction limit if you don't mention which is the wavelength you have in mind. So let's assume in the soft X-rays. So the next generation of synchrotrons are going to target a degree of coherence in the soft X-rays which is comparable to the one in free electron lasers. By definition, free electron lasers, when they are working well, they have a degree of coherence which is transverse coherence, which is basically 1. They are fully coherent. In synchrotrons, this degree is approaching 1. It's a completely different matter for the longitudinal coherence. Synchrotrons are emitting light which is not longitudinal coherent, while in FELs, this longitudinal coherent is has some large degree of.
Okay, thank you. I think it's very exhaustive answer. There are a lot of people that congratulates you, and there are other questions that I want to read. So there is a question that I'm not sure that I am understanding correctly. What determines the periodicity of the magnetic lattice?
Sure.
What is the impact if the lattice is made with progressively increasing or decreasing periodicity with a definite gradient or even amorphous?
Wow.
This is a projection in condensed matter physics.
Okay, but we are talking, I'm not sure we are talking of the same lattice. I'm talking of the magnetic lattice.
Exactly.
So let me go back to my definition. We define a lattice in jargon, in accelerator physics, like a sequence of magnets. So this is and these magnets are making the circumference of the accelerator. Now, this lattice made of quadrupole and dipole magnets, sextuple magnets, whatsoever, is typically very periodic. Not only because it's easier to build the same kind of magnets and then to replicate them along the circumference, but also because the periodicity allows you to basically minimize the impact of perturbations or resonance lines on the transverse dynamics of the particles. Okay, I think this answers some or less. More or less.
I think this answers. So there is another one. Yeah, there is one question on the electrons in the storage ring. What is the effect of time on the electrons in the storage ring? I mean, why do we store electrons in the storage ring and we don't? I mean, this is
let's say
a basic one.
We store, we store electrons, not protons or ions, because as we said, we want to maximize the amount of radiation per given total energy and magnetic field. We store electrons for a long time because, and not, I mean, for example, we don't inject and extract electrons all the time, just because we want to keep, where it is, sorry, I'm looking for the top up slide, beta motion. Please let me go back to that. This one. And we inject electrons and we try to keep them in the ring as long as we can, because we want to keep the total stored current constant over time, which is an advantage for users which want to receive a constant level of flux, of radiation flux during their experiments. And we need sooner or later to reinject some amount of charge in order to get rid of this reduction of charge because of the natural intrinsic lifetime of our stored beam. And yeah, and that's about the natural life of our beam in a synchrotron, I think.
Thank you. There is another question. Will the booster could be also used to generate some radiation? I know it could be low because it is used for accumulation energy to storage ring. Just curiosity. Assume that also emit radiation booster. How about take advantage of the radiation from the booster?
Sure. No, it's
just to bombard materials and generate heat and utilize it?
Sure, why not? Actually, in the next generation, some of the new rings, for example, take the one in the Chicago area, APS, has built a booster which is as large as the main ring. It's called an accumulator, basically, which is another quite large synchrotron, which in principle can be used as a second light source, of course. Now, there is nothing wrong in thinking of using a booster like a light source too, if you like a parasitic one. And maybe not as efficient or performing well as the main one in terms of brilliance, coherence, but still, the main problem is very practical. You have to put the beam lines around the booster, right? So it's a matter of interference of an infrastructure of the beam lines, of the booster beam lines with the main ring. But if you put, for example, the two rings on different vertical levels, you may imagine to make it. And just for fun, we are discussing at the very early stage of Elettra 2.0 design with another colleague of reusing Elettra as a low energy third generation synchro light source, injecting Elettra into Elettra 2 for a much better performance. So yeah, makes sense, but it's a matter of arranging the infrastructure in a proper way, which is not obvious.
Thank you, Simone. I think there is one question. How can crab waste optics affect electron beam lifetime?
What kind of optics?
Crab
waste. I see.
Crab waste optics.
Wow. Well, you're very
this is a very specific for you, Simone, this question.
Absolutely. Thank you for so many and so very interesting questions. Let me... now, crab waste applies, well, not a slide dedicated to that, but basically crab waste applies to, let me go to the brilliance definition instead. This could be somehow inspiring. Now, crab waste is a technique which is used in circular colliders, which is implemented through sextuplets to manipulate the electron bunches where at the point of close to the collision point. So colliders are synchrotron storage rings, but not light sources, of course. So storage rings in which bunches counter-propagating in a ring or maybe in parallel chambers interact at some given points along the circumference. In order to superimpose those bunches perfectly, sometimes you want to tilt them in the transverse plane, and this tilting is made by sextuple magnets. This is called the crab waste. The waste is referring to the perfect overlap at the interaction point of those bunches. In a collider, this kind of result is parameterized not by brilliance. They are not interested into light emission, but in luminosity, which is proportional to the capability of making these bunches to collide perfectly. Now, there is no crab waste in a light source because we are not interested into tilting electrons to collide or to superimpose in another way. But there are schemes which have not been mentioned in which we want to use deflecting cavities, which are called crab cavities, to tilt the bunches to make very short light pulses. So this is made, unfortunately I have not a slide about that. The word is the same, the technique is completely different. The result on the electron beam is similar. You are tilting the bunch either in the horizontal or the vertical plane. The final aim is different. In colliders, you want to maximize the luminosity. In storage rings, light sources, you want to produce very short light pulses.
Thank you, Simone. There are a lot of questions. Unfortunately, I cannot read them all because we are limited in time. So again, I encourage you if I manage to read more. Otherwise, you can contact Simone directly. So there is one question I want to read though. Is there a practical limit to brilliance beyond which beamline optics become the limiting factor rather than the source itself?
Wow, this is maybe a question for you, Juliana, than me. But let me say, what the accelerator physicists can do is to get to this point. This is the limit we can achieve in terms of brilliance. So and please notice that the first fraction, so the spectral flux, is determined by the number of electrons you put in a synchrotron and the kind of magnetic device you are using to emit radiation. The second fraction has nothing to do with the electron beam. It's just a matter of not that much. K can be made very small. It is typically done. And lambda is the wavelength you are aiming for your experiment. Now, from the accelerator side, how to maximize the spectral flux, what you can do is to put as many electrons as you can in a bunch and to maximize the number of bunches. There are, of course, physical constraints to the amount of charge density that you want to put in your bunch, and they are basically related to the lifetime of the electron beam, because the more the electrons are in a bunch, the more they interact each other, because they are particles with of same electric electric sign, and this means they are going to repel each other. Basically, they are scattered, and this is going to reduce the lifetime of your bunch and therefore of your stored beam. This is called Tushek scattering, driving the main contribution to the lifetime of the beam, which is the Tushek lifetime. So there is a limit, if you like. Once you get to a horizontal equilibrium emittance as small as prescribed by the diffraction limit, what you can do, and you have a given an insertion device, what you can do is to maximize the amount of charge in a bunch compatible with a given rate of injection of the top-up injection chain. So you can play with some knobs, but there is, of course, a limit, which is basically represented by the next generation of light sources.
Thank you. Yes. So why this multi-band scheme was not implementing sooner, since the advantages were well known also? This is another question.
Very good point. It was first proposed by Professor Einfeld in 1993, at least, in a paper with other co-authors. And it was not considered because at that time it was already hard to put the minimum amount of charge in a bunch to satisfy users in the third generation. The technology of magnetic lattice implied by this multiband has reached, let's say, technological feasibility only very recently, in the last, let's say, 10 years maximum, and put in operation only a few years ago. So it's not just a matter of adding or multiplying the number of dipoles in any given circumference, but the fact that these dipoles are so many, that means each of them is relatively weak in bending the particles. So you have to focus strongly the electrons passing from one dipole to another. And this implies many more and stronger quadrupole magnets, which we were not able to build in a satisfactory manner until 1 or 2 decades ago. Now we learned how to do that. And this goes together with, by the way, numerical optimization of this magnetic lattice of magnetic elements, which implies artificial intelligence, by the way. So not only that, stronger quadruples implies stronger higher chromaticity. I'm sorry. And therefore stronger aberrations, which means a limitation to the beam lifetime, which implies a different type of injection in order to put the electrons in a very small area where the transverse dynamics is stable. In other words, the concept is quite intuitive and seems to be very simple today, but its implementation has consequences on the magnetic design, on the vacuum chamber design, and on the injection chain. And all these implications were not so apparent 3 decades ago. Now we learn how to manage them.
So it's an engineering limit, let's say like this.
It's basically,
so
yes, it is.
Last question, and there's a question general on Elettra 2, and a fellow wants to measure some samples. So we ask you, Simone, when users can be welcome in Elettra 2.
Sure. The commissioning schedule, the project planning is foreseen a commissioning starting, let's say, in October this year. So the winter time will be most likely devoted to the machine warm-up. The beamlines, few beamlines will be available already for, let's say, internal testing and so on. First, external users most likely will be very welcome, let's say, from springtime and maybe summer of 2027, I may imagine.
Okay, thank you. Well, I think this is all. It's time to have a small break, and thank you very much, Simone. I mean, the audience has appreciated a lot. I mean, I received email messages of congratulation and acknowledgement.